All right, so here's the, I think this is the last example in the book, but we're going to do a couple other things after this. But this is from Bornacki, and we have a gas bell, which I guess is this thing right here, is submerged in liquid water with its mass counterbalanced with a rope. So here, right, boom, right there, and pulleys. The pressure inside, right here, is measured carefully to be 105 kilopascals. So that's just above atmospheric, and the temperature is 21 degrees Celsius. A volume increased is measured as 0.75 meters cubed over a period of 185 seconds. What is the volume flow rate and the mass flow rate into the bell? Interesting. Flow rate. Let me stop this for a second. I want to see something that's not on my page. All right, I figured out what I was doing. All of a sudden I noticed that what I had written down, I didn't write down the rates. This is a question about rates right here. All right, so anyway, we can write down what our givens are. The pressure is equal to 105 kilopascals. We're assuming that's absolute. The temperature is 21 degrees Celsius. Add 273 to that right away so we don't forget. Need to use absolutes. The volume was 0.75, or is 0.57, it still is. And there's a change, and we measure that as a change of time, as is being a volume of is being put in there. We often do measure gases, their flows in volumes, the volumetric flow rate. So just be aware of that. All right, so we want to find, according to the problem, the m dot and the v dot. Okay, so this is a dot notation. I'm not sure if we did it so yet in this class or if you've experienced it before, but this is a very common engineering thing. You have a variable that changes with time, so instead of going d whatever dt, you just put a dot on top of it. So this becomes a rate at which mass is flowing and a rate at which the volume is flowing. In this case, very simple. The volume flow rate is going to be the volume, or the change in volume over the change in time. So it's sort of there could be some instantaneous changes, like we'll find out in dynamics, right? Where we have instantaneous changes, and where then we're going to have a dv dt. But here's this just sort of like an average one, so it's just over the course of some time. So 0.75 divided by 185. So this is kind of a simplistic thing. I decided to go into scientific notation here. I usually do when it's like anywhere, when it's -2, I might actually write out the zeros and that kind of thing, but this case I wouldn't. This is how I have my calculator set up all the time, so it helps me with sig figs. It just ended up being, I got used to it, and I think it's kind of a lot easier. All right, so maybe we're going to look up, this is CO2, another thing that was given. I forgot to write out that it was CO2, so we can look up the R for CO2. We could look it up, or we can note that I think I probably wrote it down here, CO2. Yeah, we have this guy right here. So 1889. Okay, 1889. And these are kilojoules per kilogram degree Kelvin. So PV equals MRT. We've memorized that now. But we could also divide by time. Oh, wrong one. Sorry, not temperature per time. That's not really a thing. All right, and so that's the same thing as saying PV dot equals M dot over RT. There's no problem with that. So we could rewrite M dot over PV dot over RT. Let's continue with our units. So here we go for pressure. This is in kilopascals, so we want to have it in our base units. So we go 105,000, and these are newtons per meter squared. And then the V is going to be 4 V dot. It's going to be 4.054 E minus 3 cubic meters per second divided by, turn those into Newton meters instead of kilojoules, 188.9 Newton meters per kilogram degree Kelvin. And then lastly, multiply by temperature, 294 degree Kelvin. So let's take a look at our units. Newtons cancel out. Here's a square meter and a cubic meter, but there's the other meter. Okay, cool. Kelvins mess up. So we have a kilogram that's going to jump back up on the top, and we have a second underneath. Okay, so that, I believe that we have the right everything correct. We get a 7.665 E minus 3. These are kilograms per second. And we can box out our answer. So there you go. Another example down the book. Not terribly difficult. You've probably seen some PV equals MRT or NRT before in chemistry. So this is we're going to start using it for something. I'm going to make a video now, just a little demo of ideal gas law with our little toy.